Thank you, Mr. Chairman, for this introduction. Good morning, everyone. So today we'll discuss about multiferric material, and in particular, the potential of use in PV or photovoltaic application. So my name is Riad Nechache, and this work will have been done in collaboration between NAST Center in Rome and INRS in Canada. So briefly, multiferric material are oxide that exhibit at least two ferric orders. In our case, it's ferroelectricity and magnetism, and these two properties can be coupled via magnetoelectric effect, which means that you can switch the magnetization by applying external electric field and vice versa. This material have been largely investigated for data storage or for spintronic application, and the advantages here is being that the control parameter is electric field instead of magnetic field. And more recently, this material exhibit good photovoltaic properties that open a new way or alternative way to charge separation or to power or energy conversion way. So the bulk photovoltaic effect have been observed for first time in ferroelectric, and in contrast to the PN junction, this material don't need any junction to separate photocharge, since the polarization can induce a strong internal electric field that can be used efficiently to separate the photocharge. And the second advantage is that this internal electric field is not confined in a small area like in depletion zone in PN junction. This is why the name is the bulk photovoltaic effect. So the benefit here is that the photovoltaic is not limited, and they can easily exceed the band gap of the used active layer. However, until now, the short circuit current density reported until now is really insignificant, since this material is good insulator with a large band gap. So, of course, it's limiting the use of the material for energy conversion. Why we think multiferric can be a good candidate for PV application? First, because this material exhibits large spontaneous polarization. And this is really important, since we know that the photocurrent is strongly dependent on the magnitude of the polarization, ferritic polarization. Second, this polarization can be unidirectional, so we can maximize the photoferritic driving force and efficiently collect the photocharge carrier. And they have usually relatively band gap if you compare with the ferroelectric, due to the presence of electrons responsible for magnetism in multiferrics. And here I give some typical value of band gap of most known multiferrics. Bismuth ferrite around 2.5 to 2.9 eV, bismuth ferrite chromite around 1.4 and 2.1 eV, and for bismuth manganese is the smallest one, around 1.1, 1.2 EV. So here, this is a result of photovoltaic properties obtained for thin film, epoxy thin film of bismuth ferrite, And you can see that the photocurrent contribution have two origins. One from the built-in field induced by the interface, and mostly a Schottky barrier between the electrode and the ferroelectric or multiferric. And the second one is from the depolarization field induced by ferroelectricity, and this part is switchable as evidenced in this curve when you pull negatively or positively the material. So we can change the sign of the photocurrent in the film during the measurement. So this is a recent result obtained here in the epitaxial BFZ film, but with a specific geometry where the domain are organized to get in this manner here, and they got VOC of about 50 volt, and in the multi-domain system, and here in the single one they are able to go until 28 volt. So, but here this is a single domain. So here this is some controversial result, and you can understand easily that the mechanism underlying this bulk photovoltaic effect in BFO is under debate. So today we'll discuss about the BFCO case. So BFCO is a double perovskite structure, which means two cubes sharing the same corner here, and the ferroelectricity is due to the displacement of bismuth ion. And the magnetism is due to the superexchange interaction between chromium and iron via oxygen. And the nature of this interaction is depending on the structural parameter. And here I give some experimental result obtained for thick BFCO thin film epitaxially grown on STO strontium titanate oxide substrate by pulsed laser deposition. And you can see that the polarization can go up to 55 microcoulomb by square centimeter, and they exhibit a good magnetic field, magnetic moment around 1 μb at room temperature. This is due to the achievement or the occurrence of cationic ordering between iron and chromium via along the 111 direction. So this parameter, we will see in the next slide that this parameter is really important for the PV properties. Here I give some absorption properties of the BFCO films deposit at different conditions, and we variate here the temperature of growth from 550 to 650 degrees Celsius degrees, and you can see that, and we compare with the native material. This is BFO and BCO here in this different color here. So we can see that the BFCO we have a peak appears between 1.5 and 2.7 eV for BFCO. And this absorption increase when you increase the ratio R. The R is giving the cationic ordering in the film. So if R is important, that means that the cationic ordering is high in the film. And if we plot the direct optical transition of in this film, you can see that there is two linear slope, and we can that we dedicate to for example for 2 EV we give the origin of this one is coming from the ordered part of BFCO, and the 3 EV, which is close to the native absorption properties, is due to the disordered part of BFCO. So here we just change a little bit the growth condition to tune the absorption properties of this material. And you can see that we can redshift the absorption in this material when we in here we just increase the growth time of the film. So more detailed analysis suggests that the domain size of the ordered part of BFCO can affect really the absorption position in the BFCO. So more the size is large, less the small the band gap. It's like in quantum dot where the band gap is inverse proportional to the diameter or to the diameter or the size. So the PV measurement is have been performed under one sun illumination using this geometry here. We use a buffer layer of strontium titanate oxide. This is conductive perovskite structure with perovskite structure. This because they promote the epitaxial growth of BFCO on STO, and second because they can be used as a bottom electrode to perform our EV measurement. And we use 2-array indium tin oxide bottom top electrode to perform the EV measurement at different places on the substrate, on the sample. So the EV measurement give up to 4.1% in efficiency, and we get it for the sample. I mean for the structure number 1. And we got this idea to superimpose this layer to see exactly what happened for the PV properties. And we first for the optical property, you can see that when we use the multi-layer number 1 or M1 is the superimposition or combination between S1 and S2, and the multi-layer number 2 is the superimposition of 3 S1, S2, and 3. You can see that the absorption is more. I mean, the peak of the absorption is more broadened, and we have the absorption for large range of energy. And what about the PV properties? You can see that this is the geometry what we used here. So we eliminate from the bottom. In this case, we use STO subset, transparent subset STO, and we deposit a very ultra thin film of STO doped, like can be used as a bottom electrode. And you can see that from the table here, you can see that you can go up to 8.1% in efficiency. And this is really a promising and interesting result that you can, of course, we need more investigation to understand the mechanism underlying these properties. So to conclude, I would like to say that first, the optical measurement suggests that the bandgap of BFCO is related in a indivisible range, and you can be tuned by controlling the iron chromium ordering in the film. And we get up to 8.1% in efficiency under one sun illumination. And the macroscopic measurement suggests that there is a direct relationship between the PV parameter and ferroelectric properties in this material. Thank you very much for your attention.